So let's not waste any more time and give the floor to Jon.
Thank you, thank you. Goedemiddag, good afternoon. So I'll be giving a deep dive tour of JPEG XL, new image format. And I have a lot of material to cover, so I'll have to be a bit quick. It's organized in 3 parts. The first 2 parts are a bit shorter. The third part is the real deep dive, which is longer. So I'll start with a little introduction. Why do we need a new image format? Second part is, at a high level, what are the features, what can it do? And then I'll go down to the technical stuff, which I think is the most interesting part. All right, so let's start by this. Why do we need image compression, and why do we need a new image format? So here's a little back of the envelope calculation of how much data images actually are. So roughly speaking, if it's 8-bit color, then 1 megapixel is 3 megabytes uncompressed. So people often say a picture is worth 1,000 words, but actually it's more like 1 million or even 20 million words if you just compare the digital footprint of the uncompressed data. So a camera picture is actually about 200 books worth of data. So this is still quite a lot of data, considering the amount of pictures that we have. There's 2 ways to do image compression, and in that sense it's a little bit different from general compression or text compression. You can do lossless compression, which means everything is reconstructible perfectly, and for most types of compression that's the only thing we're interested in. However, lossless compression of images doesn't give you that much of a compression ratio. So for text, for instance, it's generally possible to compress text by a factor of 8 losslessly. But for at least photographic images, it's more like a factor of 2, maybe 3 if you're lucky. But for images, we can also do lossy compression, which means we do lose information, but maybe you don't see it, you don't see the difference. So with lossy compression, the compression ratio that we can get is much better, like a factor of 10, even 50. So what it means for, like, say, a typical image on the web, uncompressed, it could be like 9 megabytes, which is quite a lot. But with lossy compression, you can bring it down to a few hundred kilobytes. For camera pictures, for instance, if you would store the raw image uncompressed, say an iPhone Pro RAW image, uncompressed, this would be about 180 megabytes per picture. But if you apply lossless compression, you can halve that or even divide it by 3. If you apply lossy compression, even at a very high fidelity, you can reduce it further. So lossy compression is basically what makes images on the web possible in the first place. It is what made digital photography possible in its early years. And still, it saves a lot of storage for photographical use cases. If you look at the web, the size of the data that is getting transferred per page keeps increasing. And most of this is because of images. The text, the HTML, this is not a lot of data and it compresses well. The CSS, the JavaScript, the fonts, these do represent some amount of information, but generally this can be cached very effectively locally. So you only need to transfer it when it changes. But the images, that's where the bulk of the data is, and these, well, you can cache them, but a lot of times they are new images every time, so most of it is not cached. Okay, it's not just the web, also photography. We are now producing about 2 trillion new photos per year. So that's quite a lot of data. And besides photos, there's also things like game assets, satellite imagery used for all kinds of scientific purposes, medical imagery, cultural heritage, all kinds of things are images. So, long story short, compression does still matter, even though bandwidth has improved, storage has improved. It's still needed because we also want more images, higher resolution images. So that's why we need compression in general. But why do we need a new format? We already have JPEG. It's more than 30 years old, but it still works, of course. It was developed in the late 80s by the JPEG committee. It's a bit confusing that the committee and the format have the same name. And JPEG was an exceptionally successful format. It has lasted very long. I mean, more than 30 years in IT is it's almost it's older than Google, it's older than Facebook, it's older than all of these things, and it was very well designed, which made it possible to last this long. But well, so some people even say JPEG was a kind of alien technology from the future. Because at the time it was designed, displays couldn't even display all of those colors. The image resolutions that were available were much lower than what we do now, but still it serves its purpose. But it is starting to hit its limits. Unfortunately, we don't have the actual full JPEG standard that was created in 1992. We only have the de facto image format that we call JPEG now, which is a limited subset of the full standard. It's limited to only do 8-bit, to only do lossy, which are not originally planned limitations. The standard does have a lossless mode, it does have a 12-bit mode and so on, but it's not implemented, and in practice that means we cannot use it because you would create JPEG files that wouldn't load in a browser or in any viewer. So the biggest limitations at the moment are the 8-bit limitation, which means it's not suitable for high dynamic range photography, which requires more precision than this, and that it cannot do lossless. Also, it cannot do alpha transparency. And the compression you can get with JPEG is suboptimal. It was designed for the compute power that was available in the 90s. We can do better now. Okay, so this is an XKCD comic that I've seen very often, and it also applies to image formats. In fact, a lot of JPEG killers have been proposed in the past. Of course, there was JPEG 2000, there was JPEG XR by Microsoft. There is Google's WebP, there is the HEEC format, AVIF. But all of these also have their limitations. So in the end, they didn't really replace JPEG. JPEG still remained. And this is where I hope we can change. I have a question.
Under JPEG 2000 set complexity, what's
So it's both computational complexity at the time, at least, was a bit heavy, but also implementation complexity, because it has so much functionality that in order to implement JPEG 2000, it's complicated. It's yeah. I mean, JPEG 2000 was successful in a way. It is widely used in digital cinema and in medical use cases, for instance, but it didn't become an ubiquitous replacement for JPEG, probably because of this. Okay, so JPEG XL is yet another candidate, and I hope to convince you that maybe this time we will have something that can actually replace the old JPEG. So what can it do? First of all, we didn't start from scratch. We started by taking the existing JPEG and keeping the functionality that makes it work well. So we still have the DCT transform, 8x8 blocks. We can still do the YCBCR color space, which is translating RGB to Luma Chroma, with chroma subsampling optionally. We still have progressive decoding. So we have a lot of features from the old JPEG that are still there in JPEG XL. But we added a lot of things. So instead of only having the 8x8 DCT, we now have variable DCTs that can do different block sizes as well. We improved on the progressive loading. We added a new color space and lots of other things, and I will go into these in the next part in more detail, but basically we added a lot of functionality. So this is a diagram describing from the encoder point of view how JPEG works. It's actually relatively simple. You start with an input image in RGB, you transform it to YCBCR, apply chroma subsampling, apply the DCT transform, and then either encode it sequentially or progressively, apply some simple entropy coding, and that's your JPEG file. For JPEG XL, this is what the diagram looks like. So you can see there's more stuff, and I will go into each of these details later. But one of the big things is we can do lossless now. It's not obligatory to apply the DCT transform, which is going to be inherently lossy. And one of the things that are interesting here is that you cannot only start from an image, you can also start from an existing JPEG file and directly translate it into a JPEG XL file. So not by decoding it to pixels and then encoding those pixels again, but by directly representing the DCT coefficients. And this is a key thing that allows us to recompress existing JPEG files in JPEG XL without losing anything. Okay, I'm not going to explain this entire diagram now, but I will take some of these elements and explain them later. Point is, the original JPEG is still somewhere in there, but there's a lot of other stuff around it. So it is more powerful, it's also more complicated to implement, but it's not slower. One of the main things that are different in JPEG XL than in the traditional JPEG is that it exploits the fact that we now have CPUs with multiple cores, which was not a thing that was the case in when the original JPEG was designed. So we can do encoding and decoding using multi-threaded processing. And thanks to this, it can actually be even faster than the original JPEG to encode or decode. All right, so everything can be done on the CPU. You don't need a GPU or a hardware implementation. That was also one of the design objectives. Another key feature that I think is crucial for any new format is that it's an open standard and it's royalty-free. There's no patent licenses that need to be paid to use this. So this is, well, for image formats, I think this is essential. In video, you often see patent-encumbered technology, which I think is a problem for adoption. And also, we have a free and open source reference implementation, so anyone can use it, and the reference implementation is actually good. It's not just an academic implementation that is very slow or something like that, but it actually works and it's production ready. So another key feature that is unique to JPEG XL, I already talked about this. Existing JPEG images can be represented directly in JPEG XL losslessly. So you can convert to JPEG XL and go back to JPEG, and you get exactly the same file, bit for bit, the same file. but it will be 20% smaller as JPEG XL because the entropy coding in JPEG XL is just more advanced. So this gives a way to deal with the legacy that we have of the trillions of JPEG images that already exist. Something has to be done with them, and other formats cannot really do anything useful with them. You can, of course, decode them to pixels and re-encode them again, but then you will get additional loss, which may not be desirable if you want to preserve your heritage. So I think this is an important feature. Another thing, especially for the web, that I think is important is progressive decoding. So you don't need the entire file to show an image. If you only have the first 10 or 20%, you can already show a preview of what the image will look like that is reasonable. This is something that the old JPEG can actually also do, but in JPEG XL we have more advanced ways of doing this. And this helps a lot to make the perceived speed of decoding and of transferring images a lot better, because you will already see the image before it's even transferred completely. All right. Another design criterion that we used is we want to have a sweet spot in terms of compression at a high fidelity point. We don't think that there is really much need for very low quality images. Generally, we do have the bandwidth and storage available to afford to go to the visually lossless level of compression, so that you don't see any compression artifacts. This is a difference with video codecs, where you do need to go to lower bit rates, to stronger compression ratios, just because otherwise it would be a problem for bandwidth. But for still images, we can afford to go to visually lossless, and the codec should be optimized to have the best performance in that region, not in the region of very low quality. So that's what everything was designed for. Another, maybe more of an implementation feature than a format feature, is how the encoding works. In the old JPEG, basically the way to decide what quality to use is a manual process. You need to select, usually it's a slider where you can select the quality and you can decide whether it looks good enough or not. But the same setting on one image might be okay, but on another image it might be not okay. It's a bit image dependent what will work and what will not work. And you have to make the decision what to set the quality slider to, what to decide to do in terms of chroma subsampling. So the way the encoder gets configured is by the technical parameters of the quantization process, but it's not a visual parameterization. The same setting can produce high quality or low quality. It depends on what the input image is. For instance, images with fine text on it, they will generally require a higher quality setting to avoid artifacts than photographic images. So in the JPEG XL encoder, we did our best to make it fully automatic, in the sense that the setting you give is a visual target. How distorted do you allow the image to be? Where the sweet spot is at 1 JND, that's a just noticeable difference unit. But this basically allows you to use one setting, and the same setting will work for all images and give you a consistent quality. So this is a somewhat more technical way to look at it in terms of encoder consistency. Maybe it will lead me too far to explain this graph, but basically the variation you get in the actual quality as measured by humans looking at the image and giving their opinion, this variance is larger with other formats than it is with JPEG XL. That's basically the point. So in a sense, the encoder is more consistent in delivering the desired quality target. All right. Here is another plot showing the compression performance for lossy. On the left, you see how much bytes can be saved compared to normal JPEG. So the 0 point is whatever normal JPEG does. So you can see JPEG XL at the top there is getting you something between 40 and 50% smaller files for the same visual quality. On the right, you see the speed, the encode speed, so how many megapixels per second are processed on a single core. And there you can see that JPEG XL encoder is pretty fast, but more importantly, it's also not getting slower, or not that much, as you increase the quality. So with many of the other formats, you get a behavior where low quality encodes quickly, but high quality takes longer. This is not really the case for JPEG XL. All right. Yeah, these images on the projector don't really work because they're HDR images. So this is some subjective testing we did. And basically, the compression performance for HDR images of JPEG XL is very good in the sense that if you compare it to the alternatives, the files are 2 or 3 times smaller for the same quality. And this is, I think, an important thing to have for any future image format. Then there's lossless. Lossless is much easier to measure because you don't need humans to look at the images. So there as well, you can compare JPEG XL with, for instance, optimized PNG or with lossless WebP. But basically across the spectrum of encode speed, because you can do lossless compression at different speeds. You can do it very quickly, but not compress that well, or very slowly and compress better. But the entire Pareto front of optimal points in terms of the trade-off between encode speed and compression density is occupied with JPEG XL. So we do have a lot of encoder settings that go from extremely fast, like 1 gigapixel per second, to extremely slow, like 10 seconds per megapixel. All right. So in terms of image format features, JPEG XL basically has everything. So lossy and lossless, arbitrary precision, very good color space support, also does CMYK, alpha transparency, spot color selection mask, lots of things. It can do layered images, it can do animation, sequences, and multi-page. And this is what makes it suitable as a format that can be used across the production workflow, from capturing or designing the image to delivering on the web. All right, enough of this high-level marketing. Let's go a bit deeper now and go into the actual details of how it works. So the green and red boxes here are the 2 main modes of JPEG XL. The green one we call var DCT, for the variable size DCT. The red one, it's called modular mode. So the green one is used for lossy, the red one is used for lossless, but it can also be used in a lossy way. And it's not really 2 separate modes in the sense that the red box is used as a sub-codec for the green box. The green box itself is a superset of what JPEG can do. So basically, existing JPEG data is just a special case where all the blocks happen to be 8 by 8 and so on. Okay, so in var DCT, we don't only have the 8 by 8, but we also have all these other DCTs. I'm not going to discuss them all. So here is a visualization of the block sizes that we have. So the old JPEG only has the 8 by 8. WebP, for instance, it has the 4 by 4, 8 by 8, and 16 by 16. But JPEG XL has a lot more to choose from. And so the way it works is the encoder can decide how to divide the image into blocks. And depending on the quality target, it may use different selection of blocks. But generally, you want to use the big blocks for areas that are simple, that are uniform, and the smaller blocks for the regions that require more detail. So by splitting it like this, we can get better compression and better quality. The other thing is progressive loading. So in the old JPEG, you can do sequential coding, which means top to bottom. In JPEG XL, this is no longer possible. You can only do progressive encoding. So every JPEG XL image, at least the ones that are encoded with FAR-DCT, are progressive by default, and there's no other way to do it. You will always get, the DC, so that's basically a downscaled version of the image, first in the bit stream. There's lots of things we added to make the progressive work better, and I don't have time to go over all of them. Now we'll discuss one thing, which is the group reordering. So in the old JPEG, everything is done in scan lines, left to right, top to bottom. In JPEG XL, you can signal which order you want to deliver the data in. So you can do the default thing of scan lines, like on the left, but you can also, for instance, permute it, so that the middle of the image, for instance, or whatever region you want, comes first and the edges come later. And in terms of progressive previews, it could look like this. So this is, for instance, a 2 megabyte image where you have loaded 35% of the data. And that's what the image looks like at that point. If you zoom in, then with the default top to bottom, you will have, for instance, all of the detail of the top left corner, but you won't have the detail yet of the face in this case. Whereas if you do different ordering, you can organize it so that more important parts of the image get the detail first. Another aspect is the color space that we use. So in JPEG XL, we've created a new color space called XYB, which is modeled on the way human eyes actually work. So it's based on LMS, which is the three color cones that we have in our retina. And I'm not going to go into the details, but basically the RGB image gets converted into this XYB representation that boils down like YCBCR to Luma and to Chroma channels. But it's a slightly better space in terms of perceptual characteristics. It's going to be hard to see this on the projector, but yeah, it's very hard to see this on the projector. Anyway, the perceptual uniformity of the color space is somewhat better than in YCBCR. All right. Now, using this better color space in combination with a feature that we call adaptive LF, LF is low frequency smoothing, means that we can avoid the problem of color banding. And this is also going to be hard to see on the projector. So I will put a link to the slides and you can look at it on your own screen. So I can tell, but it's not that easy to see. Most of these show boxing or like blocking artifacts or banding artifacts. The JPEG XL one is in the middle of the top row, and it doesn't suffer that much from banding issues. There are some, but I think they're introduced by the projector. On the top right, you see what it looks like without the adaptive LF smoothing, and it looks worse. But yeah, you should probably look at this on your own monitor to really appreciate the differences. Anyway, that's the adaptive LF smoothing. There's also adaptive HF quantization, so the high frequency, which is most of the data. So I already talked about the block selection, but each of these blocks can also get its own weights for the quantization that gets applied to them. So in JPEG, you choose your quantization tables, and the entire image uses the same quantization table. But in JPEG XL, you can choose where you want to spend your bits, basically, and assign more bits to the regions that need it. All right. Okay, one other coding tool is the patches. So it's a little bit complicated to explain, but basically this is maybe a little bit similar to what some video codecs do. You can have multiple frames in an image, and even frames that are just auxiliary frames that are not part of the image itself. So if you have a screenshot like this that has many repeating elements, you can extract them and encode a reference frame that contains each of these elements once, and then you can tell, you can signal that you want to reuse parts of these in the actual image. So from the encoder point of view, you can subtract them from the original image. So what gets encoded is actually this. And you can see that our encoder is not perfect. It misses some of the repeated elements, but it can detect quite a lot of them and subtract them. So you are encoding this plus this instead of that. And in terms of compression, that can give a large advantage. So for example, let's see, as a PNG file, this was 297 kilobytes. If you would just encode it like that as JPEG XL, it would be 162 kilobytes. But if you apply this trick with the patches, you can reduce it to 87 kilobytes. All right. So this is for lossless compression, but you can also apply this for lossy compression. All right. This is probably a feature that we are not going to use for the next few years, but it's designed for the future. JPEG XL allows you to, instead of just describing the pixels, you can also signal splines, which are basically lines that are just painted on top of the image. So the idea here is that if you have, for instance, hairs, individual hairs, or lines, or cables, or something like that, you could represent them using splines instead of using pixels. And the reason to do this is because thin lines are basically the worst case for the DCT transform. DCT transform can do it, but you will need to spend a lot of bits on them to avoid artifacts. This is also why text is hard to do for the old JPEG. So if we can replace that by splines, then we can save a lot of bytes. Problem is making an encoder that effectively detects these splines and subtracts them from the image. We don't have that yet, but it is defined. The decoder can render it. This is something that we left open as an exercise for the future to try to build a better encoder that actually uses this. We also have noise generation. Noise is something that basically doesn't compress at all because it's random. It has maximal entropy, so there's nothing you can do to save bits. But noise is also something where perceptually you don't really care how it looks exactly at the pixel level. So we can synthetically generate noise instead of trying to reproduce it a pixel exactly. This is also something that the encoder currently doesn't do. You can manually activate it, but the hard part here would be to subtract the original noise from the image, and that it doesn't do yet. All right. Then we have two, what is called restoration filters. It's basically smoothing to hide artifacts. first one is what we call the Gabor-like transform. The second is an edge-preserving filter. I'll just show you, and I hope you can see this on the projector, what it looks like if you disable or enable this. So with the Gabor-like transform disabled, you can, this is at a low bit rate, but still, you can see the blockiness. So the 8x8 TCT blocks, or whatever the block size is, are kind of visible here. And the Gabor-like transform basically smooths that out. The way it does that is by doing a slight blurring at the decoder end, which is compensated by a slight sharpening before encoding. Then there's the edge preserving filter, EPF. You can see the effect here. On the left is with EPF disabled. On the right it is enabled. So the main point of this one is that it can smooth away the ringing artifacts you get close to the edges without making the edges themselves blurry. Or without ruining all the fine details in the image. Okay, then we come to entropy coding. This is what makes it possible to do JPEG recompression and save 20% of the bytes. So in the old JPEG, the entropy coding is just Huffman coding, prefix coding. There was also an option to do arithmetic coding in the original standard, but nobody implemented it because it was patent encumbered at the time. It's now no longer patent encumbered, but it wasn't implemented, so we cannot really use it because decoders still don't support it typically. So in JPEG XL, we kept the option to do Huffman coding because it's still useful if you want to do very fast encoding. But the main entropy coding that we use is ANS, which is a relatively recent entropy coding method that can bring better compression. We also have the option to do LZ77, which is similar to what is in deflate or zip or PNG. This is especially useful for non-photographic images that have like longer zones of solid color or repeating elements. And then we also have context modeling. For the context modeling, I'll come back to that later. I have way too many slides, so I'm going to go really quick. For modular mode, we have predictors and the entropy coding. We have context modeling and meta-adaptive context modeling. So the predictors that we have in JPEG XL are these 14. The ones on the top are also in PNG, more or less. The others are new ones. So what you see here is what the predictor would predict for the region that is black in the top left. It's black there because that predictor is predicting 0, which is black. But in the others, it's predicting something else. And this is useful, of course, to reduce the amplitude of the residuals that need to be encoded. We have a meta-adaptive context model that is basically a decision tree, and the encoder can choose how complicated it wants to make this tree. And this is where we get this range of effort that we can spend on encoding from very quick to very slow. So the top is a very quick way to encode, which is just using a simple fixed tree with the same predictor all over. So you see what the context looks like, and you see the predictor map, which is just the same everywhere. And then you see the residuals that still need to be encoded after prediction. So this will give you a file that is 20 kilobytes, but with more effort, you can make a more complicated tree. The context will look a lot more interesting. The predictor choices will also look a lot more interesting, but the bottom line is that the residuals that you get are much smaller. So basically, this looks darker than that. So even though you have to signal this tree, the overall file size is only 12 kilobytes in this case. All right, I really have to hurry up. I had an interlude about JXL art, which is basically using very small bit streams that produce nice images. We can do this because the header overhead is very small in JPEG XL. You can do a single pixel image in 13 bytes. So you can have a 117 byte file that looks like this in JPEG XL because the header is so small and you don't need a lot of additional data to encode this image because it's specifically designed to be small. So this is a kind of trick to produce the tree and then set all the residuals to 0 so they compress down to nothing. And yeah, you can, so this is how this looks like. This is a description of the tree, and all the residuals are 0, and the end result is that image. All right, so you can play with this. There's online tools for that. There's an art gallery. You cannot click these links here, but when I make the slides available, you can click them. Okay, so these are just some nice images, I think, that are extremely small in JPEG XL, but of course it's a bit of a trick. All right, I'm almost done. JPEG XL has very high precision, can do up to 32-bit per sample, per channel, which is way more than what we will ever need. It can do all kinds of extra channels like alpha, but also depth, infrared, spot colors, selection masks, and so on. It's also designed to be extensible in this way. It can do multiple frames. It can do multiple layers, and they are blended by the decoder, so the application doesn't even need to know that it's a multi-layered image. It will just get the blended image if it's too stupid to understand. And it can do multi-page. Okay, this is how the image is segmented into regions so that we can do parallel decoding. Not only parallel decoding, but also crop decoding. If you just want to have a specific region of interest, you can download only part of the file and get it. And that's where I want to stop in terms of the technical stuff. Sorry I went so quickly, but you can later look at the slides in more acceptable tempo. So let's go back up. These are the implementations that currently exist. So the reference implementations in C++ and Rust, and a bunch of independent implementations. In terms of adoption, we're basically in all major software now. So ImageMagick, FFmpeg, and so on, they all have JPEG XL support. In terms of browser support, it really has been a roller coaster, especially with Chrome, originally supporting it behind the flag even 4 years ago. Then they removed support again. And now, finally, they're adding it back. So hopefully, in this year somewhere, we will have universal browser support. We have it in Safari already for 2 years now. And in Chrome and Firefox, it's still behind the flag, but hopefully it will be enabled by default soon. So the support in terms of industry and open source community has been growing a lot. So it works in all of the Apple ecosystem, all of the Adobe products, and of course it was first in all of the open source software, which is always quickest to adopt new stuff. So in GIMP and so on. Krita has also been a big supporter. All right, so that's where I want to end. And here's just some pointers for future reading. Here are my slides. And if you scan that, then you can click those. Thank you.